You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The purpose of this episode is to highlight the importance of trust boundaries and isolation mechanisms in secure cloud design. In any computing system, trust is never absolute. It is granted in limited, carefully controlled ways. Boundaries mark the points where one level of trust ends and another begins, and controls enforce those separations. In the cloud, where workloads run side by side and resources scale dynamically, trust boundaries become one of the most powerful tools available to reduce risk. They confine the impact of compromise, enforce governance, and make complex environments auditable. For CCSP learners, understanding these concepts is not about memorizing technical terms, but about appreciating how deliberate segmentation and isolation transform sprawling, multi-tenant infrastructures into environments that remain defensible even under attack. A trust boundary is best understood as a logical line in a system design where different trust levels meet. At this line, explicit controls are placed to enforce separation. For example, the boundary between an internal application network and the public internet is marked by firewalls, gateways, and authentication services. Inside the application, another boundary may separate sensitive data stores from general workloads, requiring stronger access controls. Each boundary is a decision point where security must be deliberately applied. Without them, implicit trust extends everywhere, allowing attackers or misconfigurations to cascade unchecked. For the CCSP exam, recognizing trust boundaries means spotting where controls like encryption, firewalls, or authentication must be inserted to enforce separation of responsibilities. Network segmentation is one of the oldest and most reliable tools for enforcing trust boundaries. By dividing an environment into zones with distinct access rules, traffic filtering, and monitoring, segmentation ensures that not every system can communicate freely with every other. Sensitive workloads can be placed into tightly controlled zones while general-purpose systems operate in more open areas. Inspection points such as intrusion detection sensors or proxies can then be placed at the edges of these zones to monitor traffic. Without segmentation, networks become flat, and any compromise spreads quickly. The exam will often test whether you understand that segmentation is not about performance optimization, but about creating enforceable barriers that reflect risk. Virtual private cloud constructs, along with subnets, provide logical isolation for routing and addressing within provider infrastructure. AVPC gives a consumer the ability to define their own address space, route tables, and gateways, as if they had a private network within the provider's cloud. Subnets further subdivide this space, allowing workloads to be grouped logically and subject to unique policies. This form of logical isolation ensures that one customer's traffic does not overlap with another's, and that internal routing can be tightly controlled. For CCSP learners, questions involving VPCs and subnets emphasize their role in providing customer-level control over isolation, not simply as a convenience for organizing IP addresses. Security groups and network access control lists refine these boundaries further by specifying which types of traffic are allowed. Security groups apply stateful rules at the instance level, defining which inbound and outbound flows are permitted. Network ACLs operate at the subnet level, applying stateless filtering rules to every packet. Together they enforce defense in depth, ensuring that even if one layer is misconfigured, another may still block unwanted traffic. For the exam, it is important to understand that these constructs are more than just configuration details. They are the mechanisms by which trust boundaries are enforced consistently across cloud environments. Microsegmentation extends this principle to east-west traffic, meaning communication between workloads inside the same environment. Traditional firewalls focus on north-south traffic data moving in and out of networks, but attackers often move laterally once inside. Microsegmentation applies fine-grained policies that control which workloads can communicate with each other, even within the same subnet or cluster. This makes lateral movement much more difficult and reduces the blast radius of a compromise. In practice, microsegmentation requires detailed knowledge of application flows, but once established, it provides strong containment. Exam scenarios involving east-west traffic control or lateral movement prevention point directly to this pattern. Identity segmentation is just as important as network segmentation. It separates administrator accounts from user accounts and service roles from human users. Policies of least privilege are then applied, ensuring that each identity has only the access it requires. For example, a developer may be able to deploy code but not access production databases, while a service role may be able to read data but not modify system settings. By structuring identities into segments, organizations prevent single credentials from having universal power. For CCSP learners, exam items that focus on access design often test whether you recognize that isolation applies to identities as well as networks. Account, project, or subscription boundaries create another layer of administrative isolation. These boundaries divide workloads across separate administrative containers, so that policies, billing, and controls can be applied independently. If one account is compromised, its scope is limited, and others remain secure. In multi-team or multi-business unit organizations, account boundaries also provide clarity for governance and cost control. For exam preparation, it is important to remember that these boundaries are not just billing conveniences, they are isolation mechanisms that limit impact. Multi-tenant isolation is fundamental to cloud providers. Dozens or hundreds of customers may share the same hardware, but virtualization and hypervisor protections enforce strong logical separation. Controlled resource allocation ensures that one tenant cannot starve another of compute or memory. Hypervisor vulnerabilities can threaten this separation, which is why providers invest heavily in hardening and patching. For learners, understanding multi-tenancy is critical, since exam scenarios often ask whether tenant isolation is guaranteed by the provider or the customer. The answer is that providers enforce multi-tenancy at the infrastructure level, but customers must still govern their own workloads. Container isolation introduces its own mechanisms, using namespaces, control groups, and runtime policies to separate processes. Containers share an operating system kernel, which makes them lighter but also increases the importance of isolation controls. Namespaces restrict what each container can see, while control groups limit resources and runtime constraints enforce behavior. Without careful enforcement, container escapes may occur, where one workload interferes with another. Reference patterns for container security ensure that this risk is mitigated. Exam questions about containers often test whether you recognize that while they provide efficiency, their isolation is not as strong as full virtualization. Serverless computing relies on provider-managed runtimes, where functions are executed in sandboxes that isolate workloads from each other. Each function is scoped by permissions, ensuring it can only access the resources it is explicitly granted. This isolation model protects consumers from one another in multi-tenant environments, but still requires careful design. Misconfigured permissions can allow one function to escalate access or retrieve secrets it should not. For CCSP learners, exam questions may highlight serverless isolation to test whether you understand that even abstracted services still require explicit scoping of execution rights. Data classification plays a guiding role in defining trust boundaries. Information that is marked as sensitive must reside in zones with strict access controls and strong encryption. Public data may be placed in less restrictive areas. By classifying data, organizations determine where boundaries must be drawn and how strong they should be. For exam purposes, questions about classification often link directly to decisions about segmentation, isolation, and encryption domains. Encryption domains extend this principle, defining the specific boundaries where encryption keys, ciphers, and trust anchors protect information. Data at rest may be encrypted with one key hierarchy, while data in transit is protected by TLS. Keys may be scoped to particular environments or tenants. Without clear encryption domains, data can cross boundaries unprotected. Exam scenarios that discuss trust anchors or encryption zones often require you to think about these domains. Egress controls restrict outbound traffic to authorized destinations, reducing the risk of data exfiltration. Without egress filters, workloads may be tricked into sending sensitive data to malicious external addresses. Similarly, ingress controls enforce filtering of incoming requests using gateways, proxies, and web application firewalls. These boundaries create choke points where traffic is validated and monitored. Exam questions involving outbound restrictions or data exfiltration prevention highlight egress control, while those about filtering incoming requests reference ingress patterns. Finally, segregation of duties complements these technical boundaries with organizational controls. Even if networks and identities are segmented, if one person or team holds complete authority, they can override boundaries. By dividing responsibilities, such as separating the ability to provision accounts from the ability to approve them, organizations ensure that boundaries remain meaningful. On the exam, segregation of duties often appears in scenarios that describe organizational control rather than technical enforcement, reminding you that both dimensions are required for true security. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Cross-account access is one of the most important ways to manage collaboration in cloud environments without breaking isolation. Instead of merging environments or blurring administrative lines, organizations can establish limited, scoped trust between accounts through roles, policies, and temporary tokens. This allows one account to access specific resources in another without creating permanent, broad connections. For example, a centralized logging account might collect logs from multiple production accounts, each granting only the minimum role needed. This model enforces the principle of least privilege while preserving strong administrative isolation. For CCSP learners, exam questions involving federated access or scoped delegation often map directly to cross-account patterns, which demonstrate how trust can be extended without collapsing boundaries. Private connectivity options, such as dedicated interconnects, peering, or private links, reinforce trust boundaries by avoiding the public internet altogether. Instead of routing sensitive traffic through shared, global infrastructure, organizations use private circuits or direct peerings between their environments and the provider. This reduces exposure, minimizes attack surface, and often improves performance. For critical workloads such as healthcare, finance, or government systems, private connectivity is not just desirable but often required by regulation. On the exam, scenarios that mention bypassing the public internet or reducing exposure usually point toward private connectivity designs as the correct solution. Service endpoint policies create another layer of boundary enforcement. These policies constrain access to specific resources so that services can only be reached from approved networks, accounts, or identities. Without such controls, endpoints may be open to the internet, greatly expanding the attack surface. By applying service endpoint policies, organizations ensure that resources such as storage buckets or databases are never accessed from unapproved paths. For learners, the key is recognizing that endpoint restrictions are not simply convenience features but formal boundary enforcements that prevent unintended access. Secret scoping ensures that sensitive credentials, tokens, or certificates are accessible only to the workloads, environments, or users that require them, and only for as long as necessary. Instead of a universal secret that applies across multiple systems, scoped secrets might exist only in a development namespace or expire after a single session. This minimizes the damage if a secret is exposed and enforces boundaries between environments. For the CCSP exam, scenarios about limiting the exposure of credentials or reducing lifetime often point towards scoped secrets as the appropriate measure. Key management scoping follows similar logic but applies to encryption keys. Rather than using a single master key across environments or applications, organizations assign distinct key hierarchies to each workload, tenant, or environment. This ensures that compromise of one key does not expose all data. It also supports compliance, since different jurisdictions or business units may require their own key custody. For CCSP learners, recognizing that scoping keys is as important as scoping permissions reinforces the broader principle of segmentation within cryptography. Logging partitioning ensures that audit data is isolated, immutable, and visible only to the teams who need it. Without partitioning, logs may be mixed together, creating both compliance risks and operational confusion. Partitioning places logs into dedicated accounts or environments, where they can be stored securely and analyzed independently. It also ensures that attackers who compromise a workload cannot simply delete or tamper with its audit records. For exam preparation, questions about ensuring audit integrity or limiting log access often point toward partitioned logging strategies. Multi-region boundaries define how workloads fail over across geographic areas while respecting both latency requirements and data residency laws. Designing these boundaries involves careful choices. Replicating across too many regions may violate legal restrictions, while using too few may create resilience gaps. A well-structured multi-region boundary ensures that workloads can survive outages without compromising compliance. For CCSP learners, exam items about resilience and residency often require balancing both dimensions when deciding how to place boundaries. Blast radius analysis provides a structured way to think about boundaries. Instead of assuming that compromise is impossible, architects estimate the maximum damage if a workload is breached. Boundaries are then sized and designed to keep this radius as small as possible. For example, instead of running multiple sensitive systems in a single account, they may be distributed across several, each isolated from the others. For learners, this concept highlights that boundaries are not just technical. They are also risk management tools. Side-channel risk awareness addresses concerns unique to shared environments, such as co-residency, noisy neighbors, or speculative execution vulnerabilities. Providers invest heavily in mitigating these risks, but customers must understand that they exist and evaluate whether sensitive workloads require additional isolation. Awareness of these issues is part of a mature trust boundary strategy, even if customers cannot always control the underlying hardware. On the exam, side-channel risk references usually highlight the limits of virtualization and the importance of provider assurances. Policy as code guards bring automation into boundary enforcement. Instead of relying on administrators to configure boundaries correctly each time, automated policies continuously check and reconcile settings. If a boundary drifts from its intended state, for example, if a security group suddenly allows broad access, the policy engine corrects it automatically. This transforms boundaries from static configurations into living, self-healing systems. For CCSP learners, policy as code illustrates how automation supports governance in dynamic environments. Segmentation validation is the practice of confirming that boundaries are effective, not just assumed. This may involve reviewing traffic telemetry, conducting penetration tests, or simulating attacks to ensure that segmentation rules hold under stress. Without validation, boundaries can become theater present on paper but porous in reality. For the exam, questions about testing isolation or proving effectiveness often refer to segmentation validation as the correct answer. Exception management acknowledges that sometimes boundaries must be temporarily relaxed. For example, a firewall rule may be open for troubleshooting, or a developer may need temporary access to production. Exception management records these changes, sets explicit expiration dates, and requires review. This ensures that exceptions remain controlled and do not become permanent backdoors. For CCSP candidates, exam items that involve temporary access or short-term boundary changes often test knowledge of this governance practice. Documentation of trust boundaries ensures that designs are discoverable, explainable, and consistent. Without clear documentation, teams may not even know where boundaries exist or why they were placed. Good documentation allows auditors to verify reasoning and ensures that future architects can maintain consistency. For CCSP learners, exam questions about design, governance, or auditability often highlight the importance of documented boundaries. Boundary monitoring ensures that attempts to bypass or violate boundaries are detected quickly. Alerts, dashboards, and continuous telemetry can show whether unusual traffic is crossing zones, whether unexpected identities are attempting access, or whether segmentation policies are being modified without approval. Monitoring transforms boundaries from passive configurations into active defenses. For exam purposes, monitoring questions often connect directly to the idea that boundaries must be continuously observed to remain effective. In summary, trust boundaries and isolation mechanisms are not optional features but deliberate, layered strategies that reduce the attack surface and confine the damage of compromise. Whether through segmentation, encryption domains, scoped secrets, or administrative boundaries, these designs ensure that no single failure cascades unchecked across the environment. For CCSP learners, mastering these concepts means being able to select the appropriate isolation method for each scenario, balancing risk, compliance, and operational constraints. In practice, boundaries are what make cloud systems defensible, giving organizations both the technical and governance tools to operate securely at scale. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.